So today's lecture should be kind of fun. This is a lecture about different ways of doing what's called structured light scanning. So last time we talked about LiDAR scanning and time-of-flight cameras, and especially for LiDAR, that's really what you'd use if you're scanning something that's as big as a building or maybe a car or something like that. But that's not the right technology if you're scanning something that is on your tabletop, right? And we know that there are lots of things, especially for visual effects, that we want to scan that are more at the person scale. You want to scan, a prop or a, something that the special effects department has created, or you want to scan an actor in costume for later use in making some sort of a digital double. And so the key idea for most of that kind of type of scanning is called structured light. And so the idea is that what we're going to do is we're going to shine light into the scene, and we're going to look at how that light deforms from the perspective of the camera, and we use that deformation as a basis for determining the 3D shape. Okay? And this picture kind of sketches how it works. So what you see here is on the left-hand side, you've got some sort of a laser, like a light stripe projector. This could be a laser that is spitting out a very thin red line. It could be even a slide projector, like an old school Kodak slide projector with one white line that lets light come through. Or you could use a LCD or a DLP projector to basically just have a single sharp 1 pixel wide line that you project into the scene. So there are lots of ways that you could do this. Typically, I think for really high quality scanning of this type, you're usually going to find different types of laser stripes. And so how does the deformation of the stripe give us some sense of what the 3D shape is? Well, you can kind of tell that, when the stripe is falling on a surface that is kind of smoothly varying, you get smooth deformations in the image of the stripe. When it goes across something where the surface normal changes, where the first derivative is not continuous, then you get kind of a kink in the stripe. And then when the stripe actually falls on two physically different surfaces, you get a discontinuity in the stripe. Okay? And it turns out that fundamentally, figuring out how the image of the stripe corresponds to the 3D position is just basically a matter of calibration. Not that different from the type of camera calibration that we talked about back in chapter 6, I guess, right? So here's a better picture of that. So if you think about the laser stripe, and then you think about what the camera sees, right? So the laser stripe can only fall somewhere on a certain 3D plane in space. So basically, all the possible points that the laser stripe could be visible are only kind of in this sheet in 3D space. Okay, and we know that's a plane in 3D, and the image plane is also a 3D, or is also a plane, right? So what we have is a projective transformation or homography between the possible points on the laser plane and the possible points on the image plane. And so if we know the relationship between those two planes, that if I see a point in one, I can infer a point in the other. And so what I get is, kind of what I'm doing is I'm going to say, okay, I saw my laser stripe point hit here, and now I can put that back with a projective transformation into the coordinates of this laser plane in 3D, where I've kind of drawn the x, y axes to coincide with this laser plane. And so, I guess let me switch over to my piece of paper here. So, structured light scanning. And so the first method we're talking about is basically with a laser stripe. And the fundamental idea is to compute the projective transformation between the plane of the laser in 3D and the image plane. Okay, and we kind of talked about how to do that type of projective transformation estimation back in chapter 5 when we were doing dense correspondence, right? This was like the first section of the dense correspondence chapter was, if I know that the two images are images of the same plane, how do I estimate these 8 parameters that match up the two images of the plane? All I need basically are 4 corresponding points. And so, it turns out that that's not really very hard. So here's one example of how you could do it. It's not the only way that you would do it, but for example, suppose that I, have a calibration object that is made up of a bunch of planar faces, all of which are fundamentally the same. So it's like I have a thing that's built up out of the same checkerboard, and I make this kind of 3D object, okay? So now when the camera sees that object, so suppose I turn the laser stripe off and all I see is this boxes of checkerboards, right? So from the camera's perspective, that's like saying, okay, well, actually, that is equivalent to showing the camera the checkerboard in a bunch of different configurations, except I'm just seeing all the configurations in one image, right? If I assume that all the faces are identical, this is exactly all I need to calibrate the camera, because I assume that I know what the corresponding, well, so in this case, I actually would know all the corresponding points in 3D on this calibration object, because I built the object, right? So I could do resectioning, or I could do kind of plane-based camera calibration if I didn't know my calibration object very well. So now I know exactly where the camera is with respect to this object, and now I turn the laser stripe on, and I see where that stripe hits the object, and now I know, okay, from the camera calibration, I know exactly where each of these points are in the image plane, and I also know that all these points on the red stripe have to be on the same three-dimensional plane, because that's the only thing that laser can hit, right? So the laser can only hit things on this plane, and as long as I have four correspondences between the points on this laser plane and the points in the image, that's all I need to estimate the mapping from any point over here to any point on the plane, right? And so that's, kind of a simple way of doing calibration. You can do this kind of laser stripe calibration with lots of different types of calibration objects. This is only one kind of sketch, but that's the basic idea, is that first you have to show the system some sort of an object with known geometry, and you take pictures of it, and you shine the laser stripe on it, and then you kind of can tell how to match them up, right? And so basically any sort of, most of these kind of laser stripe scanning systems will give you some sort of a calibration object in the box with the scanner that you use before you start to scan anything, right? So this is the basic idea, but on the other hand, it only gives me the relationship between the laser plane and the image for this one position of the laser and the one position of the camera. And so fundamentally, this means that I can get the 3D shape of anything that happens to be sitting on this plane, but I mean, what I want to do is I want to move this stripe over the surface of the object, and that means that fundamentally what I have to do is I have to calibrate the system for every possible position of that laser plane, right? So that makes it more complicated. And so what you usually have in a real-world system is you have the camera and you have the laser stripe projector tightly coupled to each other, bolted together, right? So it's basically like one thing that has a handle, one thing is projecting the laser, another thing is is taking the picture, and I assume that I always know the rigid relationship between the camera and the laser stripe projector within this gadget. But the thing I don't know is, as I move it around, where should I put those stripe positions back into 3D space, right? So for that, I need to have some sort of fairly accurate knowledge of where that stripe should be. And so here's an example. We just actually had a demo of this device the other day in the CATS robotics lab. So this is called a roamer arm. And so what you see here is that this is the part here that has the camera and the laser stripe projector in it. And this is a robotic arm. It's like a passive arm, so it's not directly controlling things, but as you move it around, this arm knows exactly where it has been put in 3D space. So for any position of the scanning head, the super precise calibration of the robot arm tells you where you should put back that given stripe. And I have a video of that so you can kind of see how it works. So this is, again, called a roamer arm. And so here you can see that this arm has to generally be mounted very rigidly. Like, you can't shake the arm around. You have to usually bolt it to the table, and hopefully that table should be something like an optical table or even a granite table, so that if the table shakes, you're not going to lose anything. But here you can see the person is using this kind of fluidly movable scanner. It's always attached to the arm, and it's this is not exactly a stripe, this is a flying dot, but the same idea. So as you're moving the stripe across the surface, you know exactly where to put that stripe back down in 3D. And so a very common use of this kind of thing, as it's being shown here, is for things like CAD modeling and things like, so certainly you could do something like reverse engineering with this technology, where you buy a thing and then you want to make a CAD model of it by scanning it. The other thing that's very common is that you have to figure out, is the part that I have in front of me conformal to the model that I have of the part? Because if the part is a little bit thicker in one region, then it's not going to work for my industrial application. So what you often do is say, okay, here's the part as manufactured. I scan it. Now I compare it to my CAD model. I have to register it to my CAD model. We'll talk about that process next week. And then I can say, okay, well, in this region you're within tolerance, but over here you're 5 millimeters too thick, right? And so this is a very common thing to do in industrial inspection, for example. So here is, more of a visual effects application of these laser scanners. So here is a thing called the cyberware scanner. So the actor will stand on this cross, and then there are these 4 big yellow platforms that move down this gantry. And so what you get effectively, I'll show you a picture in a second, is kind of like, instead of just a single laser stripe on one perspective, you get kind of a laser circle or slice that goes around the person as the stripe moves up and down. So it kind of looks cool. It's like you have this kind of tomographic image of the stripe moving up and down the person. And so these yellow things have the laser stripe projectors, and they have the cameras inside of them. And then these things are all super calibrated against each other so that I know how to put that whole ring of data back together into 3D. And this is a kind of a similar system specifically for head scanning. So you sit the actor in the chair, you mount this, kind of opening at the head level, and then instead of the thing moving up and down the rail, this thing actually swivels around the platform and kind of does the 360-degree acquisition of the actor's head, right? So again, both of these things, in order to work, have to be extremely well calibrated. Before you do any scan, you put some sort of like calibration cylinder or block in the middle of this platform, you scan it with the scanner, and then you calibrate it, and then you put your actor into it. So here's a very young Harry Potter, standing in the scanner, not actually being scanned apparently, but just standing there. Here is from the first Iron Man movie. Apparently, Robert Downey Jr. and the crew liked the look of the scanner so much that they almost put it into the movie. So this is like they dressed the set, they put him in there, because you can imagine this is exactly what Iron Man would use to build his armor, right? Is that you want to have this really conformal 3D body map. But this didn't make it actually into the movie. But here you get a sense of the stripes and how they're projected onto the actor. And you can see, again, the deformation of the stripe gives you some clue about the shape of the object. And another application, non-visual effects, was a very ambitious effort. This is already probably 15 years ago, for digitally scanning all of the Michelangelo statues in Florence. So this was the Digital Michelangelo project. And so this was an extremely ambitious effort where they went into these galleries after hours, and they basically had to set up this extremely heavy, precise gantry after all the tourists left, and they scanned until the tourists came in the morning. And you can imagine, you can see how close they are to these priceless statues, right? So you got this, I don't know how heavy this thing was, but it wasn't light, right? You can imagine if it just kind of tipped over the wrong way and you knocked the arm off the David, it would be really bad, right? So it was extremely impressive that they even got permission to do this whole thing in the first place. And at the time, laser stripe scanning was known how to do it, but they had a lot of challenges in putting all this stuff back together. Because, unlike in a carefully controlled movie set, they couldn't afford to spend 3 hours a night really carefully calibrating the scanner. They had to get in there, scan as much as they could, and get out. And so after the fact, they had lots of challenges in trying to put back together these 3D scans. And again, with laser scanning, even though you can have a co-located camera, but it's not like you get RGB colored points directly from the scan. Because in some sense, the thing that you're scanning is kind of washed out by the red light, right? So you can turn the laser on, turn the laser off to get kind of co-located RGB images, but in terms of the 3D points, you really do get, again, the same kind of like angry cloud of bees I talked about last time, where you just got a whole bunch of 3D data, and now you have to figure out how do I put all that data back together into the same frame of reference. So that can be tricky. And the ambition of this project, as I recall, was to scan the statue at a sufficient precision to be able to discern the chisel strokes of Michelangelo, right? So they really wanted to scan this at super high precision. Because you can see here, the stripe is not very wide, right? So you can imagine how long it must have taken them to scan the statues at that kind of precision. And of course, statues are really not made, obviously, for making it easy for you to scan, right? And so they had lots of issues about, okay, well, how can we possibly place the scanner to get into these nooks and crannies of the statues that are not easily visible, right? Maybe you can see them, but can you mount your heavy gantry in a way that the laser can probe up into the statue? So it was extremely challenging. I think that they augmented this with handheld laser scanners that collected data in places that were harder to reach, but then you have to figure out how to register those scans against the other scans, right? So there's another technology called the Polymus scanner, for example. That's a scanner that, again, projects a laser stripe, but there are different versions of it, but the one I'm thinking of has basically kind of something that's equivalent to it's kind of like a magnetic motion capture register system. It's almost like combination of a GPS or IMU or something like that for an indoor scanner. So basically, you put this block in a place where you know where it is, and then as you move the scanner around in 3D, the combination of the scanner magnetically talking to the block and some sort of inertial measurements gives you a sense of where you should put these stripes back. And so if you watch, I mean, people get scanned with this all the time. I remember there was a time when they scanned Stevens Colbert with a laser scanner, and then they gave everyone the scan to do fun things with, right? So, right. So that's basically the fundamental idea behind moving this laser stripe around. Again, the caveat right now is that you have to know very carefully where your stripe should fall in 3D space to put all these stripes back together. So it's a little bit tricky to do like a homebrew laser scanner because you have to do all this super precise 3D, calibration. But these are the kinds of scans that you would get in a, Hollywood production, right? So you'll put the actor inside the cyberware scanner, you'll scan them, and then you can get very accurate. One of the reasons that you do this for sure is things like making digital doubles. It's also good just for general, costume reference about how is this fabric hanging on the person that day? How do we make up that person? How much did this makeup apply and stick out from their face? Because you can do 3D measurements of that kind of thing now. So, they do this for, I think it's almost routine these days where, the scanner is just sitting off to the side of the set. When you're not on set and you're in costume, you might as well just stand there for a minute and get scanned, and then they put that data into a file, and maybe they use it and maybe they don't. But it's not too burdensome to sit there and be scanned. So here are various scans. This guy from Scott Pilgrim. This is a guy from Thor, one of the Frost Giants. And again, this is the kind of level of detail that you would get from these kinds of scans. Again, you're getting things that are basically, millimeter accurate at least, maybe more. Because you can, and I'll talk about this in just a second, you can localize that laser stripe, the center of that stripe, pretty much in detail. And as you sweep the stripe across, you can kind of get, very high quality scans. And there's not really noise to speak of in the same way that you get with anything that was image-based. I don't know precisely whether this and this were taken with the very same scanner. It could be that this is from the head scanner and this is from the body scanner. I'm not totally sure. These are all courtesy of Gentle Giant Studios, which does all sorts of 3D scanning for Hollywood. And I'm going to show you some pictures from my visit there at the end of the lecture. Here's the Predator. Again, you can see here that laser stripe scanning has some of the same problems as LiDAR scanning does, in the sense that the laser stripe, or the projected laser stripe still has to be visible from the perspective of the camera. And so here, I'm not sure what you'd call these. I guess the Predator dreadlocks. I mean, there's all sorts of nooks and crannies, and maybe that's really dark, and so maybe the camera didn't see the stripe in this region, and so you just don't get any returns here. So again, the best case scenario for laser stripe scanning is pretty similar to the best case scenario for LiDAR scanning. Get some nice matte white, not super shiny thing, right? This is a guy from Sucker Punch. Again, the thing that's really remarkable about these scans is the level of detail that you can get. I mean, it's really kind of cool to see all the folds of clothing, all the wrinkles in this guy's face. I mean, you can really pick up some nice detail. It doesn't really work very well with hair, as you can see. Like, here, you can see that hair just generally doesn't work so well. And you'll see with our scanner here that you're not going to get too much great hair either. And you also do it for things like props. And so again, the nice thing about props is that you don't have to wait for the person to stay stationary. You can scan this prop as many times and in as many ways as you want. So you got swords and jetpacks and the Loki helmet and so on, right? So pretty much any prop that you'll see in Hollywood has probably been scanned in. Again, just like, well, nothing's happening, this stuff is sitting around on the set, just scan everything you get your hands on, and maybe the effects companies use it and maybe they don't. Okay, so like I said, you can do what's called space-time analysis. And actually, before I do that, let me just talk about one other thing. So here, this is a picture of a slightly different kind of structured light scanner, but this one has a projector of a pattern or a stripe in the middle, and then it has two cameras on either side. And once you've got two cameras, then life becomes a lot easier, in the sense that you can calibrate these two cameras together as if they were a stereo rig, and then you can calibrate them against the laser stripe. And so this is the kind of situation you have here, where if you have two calibrated cameras, and you say, okay, well, I know where these cameras are in 3D space, and I can calculate the epipolar geometry between the cameras, so that's what these diagonal lines are. So if I know the epipolar geometry, I know that having correspondences between these two cameras if I know where they are in 3D space, I can triangulate through them to get a 3D point, right? And so the laser stripe, or the pattern that you project into the scene, is just a means to an end to finding a good correspondence between these epipolar lines. So it's like saying, okay, well, if I shine a laser stripe that's kind of horizontal onto the scene, then, you know, if I didn't have the epipolar lines, I would say, okay, well, I know that, you know, the laser stripe here probably corresponds to the laser stripe here, and I know exactly which point corresponds to which by cutting that laser stripe with the two epipolar lines. And so now I have, for every position along the along every pair of conjugate epipolar lines, I know exactly where I am, and since I know where the cameras are, I can triangulate that point to 3D space. I have the same kind of issue as, you know, as I move that whole rigid rig around, I still need to know where do I put those points back. But this is kind of nicer in the sense that the 3D, that the structured light is really only there for putting some texture on the scene that gives me some unambiguous correspondence on the epipolar lines. And so let me talk about one more thing, and then I'll show an example of that. Let me see what my videos look like here. So I have, it's not exactly this. Let me first talk about one other thing. So the other thing I want to talk about is called space-time analysis. And so the idea is that if I have everything really nicely calibrated, what I can do is, instead of just trying to see the image of the stripe and find the center of it, what I could imagine doing is I slowly move my stripe across the surface of the object, and every image of the stripe probably has kind of like this Gaussian, you know, pattern, right? So I mean, if you look at a laser stripe, it's not like it's just a binary thing. You know, it fades off at the edges and it's strongest in the middle, right? So you imagine that if I slowly move the stripe across the surface of something, I can look at, over time, what is the intensity of the stripe as it passes across my pixel, and then I could very accurately localize where the center of that stripe was, right? So that kind of gives me sub-pixel resolution that I can get by space. It's called space-time analysis, right? Because it is, I'm doing some sort of temporal motion of the stripe, and that gives me much more accurate localization of the center of the stripe. And so here's an example of how that works. So this is the work of Li Zhang back at the University of Washington. And so here we can kind of see is you've got a pair of stereo cameras, and you've got this pattern of stripes being projected onto it. And again, these stripe patterns are fundamentally random, right? Because you don't really care what you're projecting. You just want to be able to get matches along the stripes. And so this is the kind of thing where you can get reconstruction from stereo. I think that, you know, there are some other pictures like this where, again, you've got two cameras and you've got this moving pattern of lights. And you can actually do this. I think, I don't want to speak for this. I don't know whether this is real time or not. This may not be real time, so I don't want to say that it is. I think there's some more pictures over here. Again, same kind of idea here, where you've got, you know, this is a case where you're moving the light stripe across the surface slowly, and you get this nice image of an object. So we're going to talk in a second about what's the deal with these colored stripes. But here are some examples of, this is kind of what I was talking about, is that you move the light pattern slowly over the surface, and you use that to very accurately triangulate where the stripe is. So let me just talk for a second about you know, some of the challenges of stripe scanning. So one of the challenges is, okay, well, couldn't I do better by, you know, couldn't I do better by, instead of having to move this single stripe over the surface of the object, why don't I just project like lots of stripes on the object at once, right? So let's say I have a device that projects 50 red laser stripes onto the object, and then I get 50 slices of the object all at once, right? Why wouldn't I want to do that instead of having to laboriously move the camera, move this laser thing over the surface of the object? Well, one of the reasons is that it turns out to be very difficult to disambiguate which stripe is which if they all look the same. And so here's an example of saying, okay, suppose I've got a stripe projector that sends out these 5 stripes, and here's what the camera looks at. And so the camera is sending them out in the order 1, 2, 3, 4, 5. Here, you know, the camera sees them in the order 1, 4, 3, 5. And so what happened? We lost stripe number 2, and stripes 3 and 4 switched places because this object was closer to the camera, right? So if all these stripes look like red lines on the object, there's no way to disambiguate which stripe is which, right? You need some sort of way to code the stripes in order to be able to unambiguously tell this is stripe number 1, this is stripe number 2, this is stripe number 3, right? And so that brings me into the next idea. So one of the ideas that you can use is called time multiplexing, okay? And so the idea is, instead of just looking at one image of one stripe, what you do is you shine a bunch of patterns onto the object that are all a little bit different, and then you say, okay, how did the time progression of these patterns uniquely give me a position in space? And so here's kind of an example of what I mean. So here is a 3D object, and what I've done is shown 8 different patterns onto the object, right? And these are kind of like binary patterns that increase in how often the white and black alternate. And so here at this red dot, what I could do is I could say, okay, well, at this red dot, the pattern of dark and light, or off and on that I see, looks like this. I see black, white, black, white, black, 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 white, okay? And so the idea is that if I arrange these patterns in a certain way, there's only going to be, so basically you can see there are 8 possible on-off positions corresponding to the 256 finest stripes that I've got. And if you go back and think about it, the way that I've constructed these patterns says that, for each one of these 256 stripes, the on-off pattern of these 8 images is unique, right? And so that's kind of clever, where basically I just say, okay, and I don't have to show 256 patterns to get 256 stripes. I have to show log 2 of 256. So I only have to show 8 patterns to get 256, and I would only have to show 9 patterns to get 512, and so on. At some point, you become limited by how finely you can project your stripe, right? So for example, I'm doing this with a standard off-the-shelf projector, and at some point you run up against the width resolution of the projector, and also how well you could even tell different stripes apart, the black to white transition from the perspective of your camera, right? So there is a kind of a physical limit on how well this could work, right? Even if you have the highest resolution camera in the world, just because of the way that the light diffuses from the edges of the projector, you're probably not going to be able to get like 2,000 stripes on the surface of an object, right? Another kind of minor note about this, so these patterns that are uniquely decodable are called gray codes. And so this is a sketch of what those black and white patterns looks like. And I think that the homework problem I assigned is basically how do you generate these gray codes. It's not very hard to do. They're basically just alternating patterns of black and white that are shifted by half a period, kind of. And so the idea is that another nice thing is that each of these patterns, if you think about, if you go back and figure it out, each stripe and its neighbor only differ by 1 bit of difference. And you're going to prove that in the homework. And that makes it easy to kind of tell which pattern am I at, because you're just looking for which bit has flipped as you move along the sequence. And again, if you get stripes that are lost or mixed up, doesn't matter, because you have this uniquely decodable position of the stripe, right? So now every on-off pattern that I see uniquely tells me which stripe was I at. And so I can now undo any sort of weird mixing and matching and losses that I got from the projection. So one thing that's a little bit tricky in practice is that you might think, okay, well, this is really easy to tell if for the image of the object, am I in an on stripe or am I in an off stripe? But actually, that's not necessarily so easy. So for example, it depends on the color of the object itself, right? So in this case, let's look at these pixels, red and blue. And so red and green. So here, the intensity at the red pixel when it's on is 137, and when it's off is 3, okay? And that's because this lies on this kind of a darker patch on the surface of this jug. Whereas on the green dot, this is on a bright surface, and so when this is on, I get 226, and when it's off, I get 18. So the on position is like almost 100 levels brighter than the on position at the red dot. And so that means that what I should really be doing is making a per image location threshold for what constitutes on and off. Because if I use the same threshold across the entire image for on and off, it may be that, for example, if I have a really dark region of the image, then I would always think it was off, because it would never get brighter than you would get for a bright region. So the smart thing to do is to basically make a per pixel threshold for what that should be. And the easiest way to do that is fundamentally to, you could collect 2 extra images. So if you're scanning something like a prop, you could spend all day showing patterns on the prop. There's no downside. So one thing that you could do is you could say, okay, I'm going to take an all-on picture, like this picture on the left, and an all-off picture, like the picture on the right, and then I'm going to choose the per pixel threshold as the average between those two images, right? And that gives me the per pixel threshold that I need once I look at the stripe pattern, right? So I know what on looks like, I know what off looks like for every pattern, or for every pixel. The other thing that I could do that actually is arguably a lot simpler would be, instead of that, what I could do is for every pattern I show the pattern and I show its opposite, right? And I just can tell whether it's on or off by which one is darker, right? So here in this case, it's like saying, okay, here's one of the patterns from the gray code earlier. It's like saying, okay, let's take this guy, and you know, I show that and I show its inverse, and I say, okay, well, the first image at the red dot had a brighter intensity than at the dark dot. So I know this was the on image and this was the off image, right? So, you know, again, they're not actually necessarily measuring any thresholds. I'm just saying which one is lighter or darker. But this one actually requires me to show twice as many patterns because I'm showing every pattern and its opposite. Whereas the other method would require me to show all the patterns plus an all on and an all off, right? But again, when you've got all the time in the world to scan, you can try all sorts of things, right? This will not work for a impatient Hollywood actor for a couple of reasons. You know, one is the impatience, and the other one is the fact that you cannot tolerate motion of the object while you're shining these stripes on it, right? So I mean, it's very difficult for somebody to stay still as you shine, you know, 16 light patterns on them, and you'll find that if you know, then you'll get these weird 3D deformations that come from, you know, even if you've got the most patient actor in the world, even just subtle things like breathing is going to change the 3D surface of the object, and that may give you some really weird results, right? So, I mean, actually, to be fair, that's also true for even just the laser stripe scanning, right? So if you're scanning somebody and they shift or move as the scanner is moving up and down, well, then you're going to get these little waves or jigs that, like, you could literally see sometimes the breathing profile that comes from the stripe moving down the person's chest. And so there usually is, you know, a little bit of cleanup that you have to do on these scans to remove these kinds of jiggles. And so, as I'll talk about in a second, you know, when you hire somebody to do these scans, you're not just hiring them to physically drag the scanner out there and do it. You're also hiring them to touch up the scan in a way that's going to be important and useful for the visual effects artists later on, right? Yeah. Okay. So another kind of a neat idea that is kind of related to these on-off patterns is this is a paper from many years ago, but I always like this Hall, Holt, and Rosenowitz paper. It's called Stripe Boundary Codes. And so the idea is that, you know, instead of trying to find the center of each stripe, what I could also do is I could say, okay, I encode the position of a stripe by looking at what happened on either side of it. And so, for example, here, the idea is that I would show these 4 patterns of stripes on the object, right? So I'm only showing 4 patterns, and what I do is I say, okay, you know, let's look at the line between the first and the second stripes. And so the idea is that here, the change from 1 to 2, basically I had a 0, 0, right? Here I have a 0, 1, here I have 0, 0, here I have 0, 1, right? And the idea is that this pattern of 4 on-off pairs only occurs once if I think about going across the entire stripe, right? And so it turns out that I can encode 110 patterns of on-off looking at the boundary between the stripes, not the center of the stripes. Because if I look at the center of the stripes, there are lots of stripes that are like black, 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 right? I can probably find another black, 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 black somewhere in this pattern, but what I'm looking at here is the difference between, you know, black, 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 black on the left and black, white, black, white on the right. And there's only one of those, right? And so instead of having to so this gives me 110 patterns, log 2 of 110 is closer to 7 than it is to 4, right? So the idea is I've saved some patterns by thinking about, you know, adjacent stripes instead of just the stripe itself. And then, you know, the next obvious thing is, well, couldn't I do even better if I allowed myself colorful stripes, right? And that's definitely also true. And so if I allowed myself to do red and green and blue stripes instead of black and white stripes, then I could show even less patterns. And in fact, Kim Boyer, our department's head's, you know, PhD thesis had to do with colored striped structured light scanning, right? That was one of the first color structured light papers. And so here's kind of an idea of how that kind of thing works, where, again, what you do is you shine a unique pattern of color onto the object. And so the cool thing about this is that all I'm doing is I'm shining this one colorful pattern once onto the object, right? there's no need to shine a bunch of different patterns on the object. I just show this colorful pattern, and the idea is that every 3 stripes is unique, right? So there's no other blue, green, blue pattern anywhere in the rest of the sequence, right? So when I see blue, green, blue in my image, I know, oh, that was stripe number 5, right? So this unique alteration of colors tells me the stripe index. It's a very clever idea, right? And so this kind of thing is actually based on a mathematical theory, and I'm not Dutch, so I'm going to screw it up, called a De Bruijn sequence. And so the idea here is, what you're doing is you're trying to construct a set of numbers such that within this set, you never get a repeat. And so here's just like saying, okay, so if I give you 4 symbols, 0, 1, 2, 3, and I insist that no pattern of 3 numbers appears more than once, this is such a pattern, right? So if you look at this, there's no other 0, 0, 0 anywhere in the sequence. And not only that, every possible 3 symbol pattern occurs exactly once in the sequence, right? And so here, and that's even true cyclically, right? So here it kind of wraps around. So the last one here is 3, 3, 3, and then if I have another repeat of this pattern, so if I look at this wrapping around, 3, 3, and then back to 0, there's no 3, 3, 0 anywhere in this sequence until I get to the end, right? And so the idea is that what I have is, for example, if I have 4 symbols and I require no 3 of them to repeat, then I have a 4 to the 3rd power 64-bit, or not bit, a 64 length sequence of symbols, and that can be converted into a color stripe code like this. And so, one of the homework problems, I think, is to find me a simpler such sequence, like 3 patterns, or 3 symbols and no 3 of them repeat, so you should be able to kind of monkey around and find a way to get these 27 numbers in such a way that they don't order. And so that's actually a really neat mathematical idea. And in fact, I read there's a guy who did a magic trick based on this De Bruijn sequences, which was really clever. So basically, he memorized the order of, he transferred one of these De Bruijn sequences into the order of the cards in a deck, right? And so then he would say to anybody, okay, well, take a card out of the deck, and then you can cut it as many, you can cut it as many times as you want, and then he just kind of riffles through the deck, and he can tell you what, and what was it? So take the card out, put it back in, then you look at this, and he can find the one thing that was out of the De Bruijn sequence because he knows that, their cards have to occur in a certain order, right? And so it makes it seem like it's impossible that you could somehow do this, but all you have to do is memorize the sequence of the cards and keep this in the back of your mind. And so how would you use this in practice? Well, the idea is that you shine this colored stripe pattern on the object, and then you take the known pattern that you projected, and then you look at what you actually received, and you can match them up, right? So then you could match them up, imagine using dynamic programming or something like that. And here, this image kind of suggests the fact that actually it may not be totally easy to match them up, because the image of the stripes is never going to be as beautiful as the solid stripes that you projected, right? So here, you can say, okay, well, I know that the order here is like black, pink, blue, and here's the black, here's the pink, here's the blue, but it's definitely not such a great, beautiful color, right? There's lots of weird variation inside here. And again, that comes from the fact that you're projecting this color stripe pattern onto a possibly colorful object, and so when I shine a red light onto a green surface, I'm going to get something that looks like a muddy, crappy color, not red, right? And so that makes it a little bit tricky to figure out how to tell what color has actually been projected onto the object. So that's a problem that you don't have when you have something like black and white patterns. Even if you don't get precisely black or precisely white, it doesn't really matter, because all you have to know is whether it's on or off. For the color sequence, suddenly it becomes more of an issue to figure out what color did I really put on that surface. And then again, you have the same issues here with if the stripes are missing or switch places, then, well, if they're missing, you can probably do okay, but if they switch places, you can't just simply use dynamic programming. You probably have to decompose the correspondence into simpler pieces. If you remember back to the part in dense correspondence where I talked about how do you correspond along epipolar lines when you may have switches due to this double nail illusion, that's the same kind of problem that you're faced with here, right? And so, again, you may have to do multiple steps of dynamic programming in order to disambiguate this. There's also a way that is kind of like a hybrid between So here, so far what we've been talking about is basically hard-edged stripes, right? You know, just step function-like projections. Another kind of way of doing it, so let me just go back and talk about this for 1 second. So one thing I forgot to say is, what is the advantage of these colored stripes? There are possibly lots of problems, but the advantage is that I can actually just show this one pattern at once, and I get, I don't remember what the number is, this pattern, I believe, has, I'm trying to find the number, 125 unique stripes, right? So basically what I'm doing is I shine this color pattern on, and I get 125 3D positions, right? And since I only have to shine one stripe on the surface to get the 125 numbers, I can basically do that at frame rates, right? So what I do is I have a moving object, the color pattern is always the same, and I can basically reconstruct the 3D shape in real time, right? I mean, maybe the reconstruction isn't exactly real time, but I can record the pattern moving in real time and reconstruct it later, right? And so this is what you would call like one-shot scanning, where instead of having to shine multiple patterns of light on a stationary object, you have only one pattern of light and you get the 3D immediately, right? And so that's the advantage, is that you can basically do, you know, scanning of things that are moving, right? You don't have to worry about how do you put the stripes back together because there's no ambiguity. You just get one nice picture of a moving object. The same kind of thing you can do with what are called these fringe patterns. And so here, what you've got is, instead of sharp-edged objects, you have what looks like, you know, if you were to plot these from the side, you would see like a cosine wave. And the cosine wave is shifted by 3 different phase shifts. And if you show the cosine wave in, you know, succession, what you get are basically 3 continuous numbers, not just black and white patterns, and you can use that to undo what was the 3D position of the point. The really cool thing is that, you know, for this you need to project 3 patterns onto the object, right? And so one thing that someone realized is that the way that your high-quality color, you know, DLP projector projects a 3D image is not by having, so there's only one lens on your projector, right? So what's happening? Inside the projector is this thing called a color wheel that is spinning extremely rapidly, right? And so instead of getting all the RGB at once, what you're really getting is a frame where white light is being shot through a red filter, then that filter spins around and you're shooting through a green filter. And so what you're getting is the projector is sending out RGB, 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 RGB at some high frame rate, like 120 hertz, right? And so the color wheel is spinning really fast. And so the observation here was, well, you could do really, really fast structured light if you just removed the color wheel from the DLP projector, and then you kind of told, this is the R, this is the G, this is the B. The projector is going to show those things for you in quick succession, and then suddenly you get extremely high frame rate structured light by using the mechanics of the projector. And so that was a really slick idea. I mean, you have to be a little bit handy to take apart the projector and remove the color wheel, and you know, that's not something for the faint of heart. But once you do it, you have this kind of unique, you know, opportunity to get very high frame rate structured light. And so that's a pretty cool idea. Okay, so let's talk a little bit about like real world stuff, right? So first of all, let me pause to ask any questions about the theory. Okay, so let's talk a little about, you know, what people are doing with structured light these days. And so one very common structured light thing, so this is, so you guys know about the Microsoft Kinect. We talked about the new version of the Kinect last time, which is really a time-of-flight technology, but the Kinect version 1 was actually a structured light technology. And so it wasn't projecting stripes into the scene, it was projecting basically kind of like a random 2D dot pattern, or a pseudo-random 2D dot pattern in the infrared world, right? So if you were to look at the living room bathed in infrared light by the Kinect, you would see lots of little dots. And the idea is that these dots are not totally random, because every point in space, if you look at the local neighborhood of these dots, you know, it has a unique neighborhood of dots. It's kind of similar to thinking about the unique neighborhood of color stripes that define a particular position. This is kind of done in a 2D world where you say, okay, if I see this dot and I look at all my dot neighbors, I know where that projection was from the perspective of the scanner, or from the projector, and that gives me a 3D triangulation because there's an image of those dots. So actually, that's the way the Kinect version 1 looked, and actually this is not from that. This is a picture of what's coming off of the new Google Tango cell phone, right? So that just was announced beginning of the semester in January, right? That's a cell phone that basically is doing real-time depth sensing, and someone looked at it in the infrared, and this is what they saw. So basically, the new Tango phone is fundamentally using what used to be inside the first version of the Kinect. And so you can think about this as a structured light technology, right? So I didn't really talk about it here, but you could kind of take all the stuff I talked about and extend it into 2D, right? So instead of just having a single vertical stripe, you could do like checkerboards of colored stripes in space and give you, and get even more localization ability. So this is kind of the dot pattern that you see from a device like that. So here are a couple of devices that, and one of them is over here. So I wanted to buy something that basically did kind of quick, dirty, 3D scanning. And so here's one thing I considered. This was called the GoScan from Creaform. And so what you see here is it's got a projector of a pattern, and this is not really a laser stripe. It's really much more of a black and white checkerboard that you see being flickered onto the scene. And so it's probably a proprietary pattern, but the idea is the same as like the dot pattern, where you know that if I see a certain region of checkerboard, I know what corresponds to that in my projection. So seeing a certain point on the checkerboard pattern tells me how I should reconstruct that point in 3D. And so here's an example of the scanner that I brought today. This is the Artec EVA scanner. And so we'll do a demo of that in just a second. But the idea is the same. So here you can see that it's got, it's got a camera, or I guess maybe it's got one or two cameras, and it's got a projector of light. And actually, in this one, it's projecting some sort of light pattern, but you can't even really perceive what the pattern is. I mean, it looks just like white light, basically, at a very high strobe rate. So if any of you have any sort of epilepsy, seizure problems, you don't want to get scanned by this thing. So we'll do this in just a second. I also wanted to mention that, so my friend Sophie Kahn is an artist, and so she makes art out of 3D scans, and one of the things that she's really interested in is kind of the kinds of glitches and the mistakes that the scanner makes. And so instead of trying to make these beautiful scans that you would use for visual effects later on, she's kind of interested in weird scanning artifacts and chunks of 3D that you get and things that you don't get. And so I encourage you to go take a look at her work. And then so she scans people and objects, and then she 3D prints them, and it's a really striking effect. So definitely cool to look at. Okay, so let's do some scanning. So let me unplug my one thing, plug in the other thing. Okay, so again, what we're going to see here is the Artec EVA scanner. I can probably close this thing. Okay, so again, if you're a flashing light person, you're going to be freaked out. And so what you see here basically is this kind of histogram bar thing at the left is telling Austin kind of the sweet spot where he should be for scanning. So if he goes, if this collection of returns goes too far outside the range, then he's not going to get any results. And so what you're seeing here is basically real-time images from the scanner that kind of lets you get a sense of, am I getting good returns? And so here we're scanning this bucket, and you can see it looks pretty good. I guess what we're not getting is the handle of the bucket. You can see is kind of coming back as no return. And now he's actually starting to scan the bucket. And as he moves around, the cameras are being used to, in real time, register the the scans together. And so what you get is basically a real-time 3D plus texture scan. So it's pretty slick. And then, of course, once you're done with the scanning, you can take this thing and turn it into a 3D model. You can see the points that came back from it. And there's all sorts of, once you're at this point, you can definitely do all sorts of things like, clean up the mesh, remove stuff like this on the ground plane that you don't want. But the texture mapping is, pretty reasonable. So does someone want to be scanned? All right, come on up. Let's go over. Have you got a space there?
I guess that's over here.
Maybe over here. Yeah.
So I want to close
Yeah, close your eyes. Maybe that would be good. And try and stay as still as possible. So this is just a preview, right?
Yeah, this is
Okay. Yep. Go ahead. And actually, you can see here that basically, her coat is good, her skirt is good, but the hair is not coming through very well. And that's something that, what you need to do to fix that is something like, right, you can see this is, tracking is lost.
I'll read it back.
All right. So this is fine. Right? So what basically happens is we got a partial scan. Actually, you can kind of look at this while we're here. So how do I move the...
You just turn around. Just want to move the...
I want to kind of do the hand, to drag it. Is there a...
both button click.
Both button click.
Yeah.
I see. Okay. So you can see that, even though actually the density on the face is not like amazing, once you texture map it, it looks pretty good, right? And so you can see we didn't get a lot of results on your hair, and but the rest of the fabric, fabric is really pretty solid for this kind of thing. And again, even though the 3D may not be necessarily great, once you texture it up, it actually looks pretty good. And so we can try and scan you some more. And then the idea is that once you've got a bunch of scans, you can register them together into a full model. So it's not like if you don't get it all the first time, you're totally stuck. So I don't know if you want to scan. Of course, now you've moved a little bit, right? So now it would be tough to register your non-rigidness, but that's the idea.
I have a built-up model on my computer if you guys want to see after class.
Yeah, so afterwards we did do some scanning of people in the lab, right? I'll try again. Anyone else want to get scanned?
I'll get scanned.
All right, come on, get scanned.
I'm just always the first to volunteer, so I got to hang
That's
back.
true. So the interesting question here is going to be, so before we start, we can kind of predict that, like, I don't know what's going to happen on the glass. Well, keep the glasses on. Let's see what happens.
Yeah.
And the rest of you looks pretty good. Hair may not work.
Thank you.
Yeah, it looks good. All right, so let's try it again here. Don't move, but you can open your eyes if you want. Uh-oh. Lost tracking. So part of it is just that we're scanning in kind of this weird constrained space. Yeah, I mean, I think that if we had a little bit more range of motion on the scanner, we would do better. So like, again, this I felt came out pretty well. So like actually, even through the glasses, we were getting pretty good results. I'm not sure where the 3D points actually are. And so,
Yeah,
it's not bad.
I think the glass is too reflective when the light is...
Yeah, when the light hits it, so maybe some of this stuff is coming from the side, right, instead of getting the head-on thing. But you can see, again, to really get all the nooks and crannies is tricky, right? So like getting under the chin, getting all the folds of your jacket may be tricky. But, I think for the most part it looks pretty good. And so, those of you that took like CAD classes, right, would be able to reverse engineer this into a nice mesh, right, clean up all the holes. And then once you've got that, then you could, do the watertight, mesh, and you could print it, right? So one thing we're talking about would be a lot of fun to make, like, lab action figures, right, where you do everyone's scans, and then you can 3D print them out, right? So once you've got them, you can do whatever you want with them. Okay, so let me just say, so I think we can do a more scanning later if you want, but let me just finish up by saying that, so let me talk a little bit about my trip to Gentle Giant Studios in California. So this is a company that does basically 3D scanning for all sorts of movies, right? They've scanned any actor in any set that you can imagine. But in addition to that, they also have lots of highly trained classical sculptors and digital artists. And so the other great thing about this company is that fundamentally they not only make scans for movies and so on for visual effects, but those same scans are used for video games, toys, like all the toys that you would see as movie tie-ins come from these 3D scans. It used to be, when I was a kid, you'd get this pitiful action figure that didn't look anything like the actual person, right? Now, the action figures you get look pretty good because they come from the same 3D scans that were taken on set, fundamentally. And so here, this woman, it's hard to tell, but this is a character from the first Star Wars, right? So this guy here is one of the guys who gets force choked out, this guy. And so, he's no longer around to make a great action figure of, right? So this woman is very carefully sculpting, this person from clay or from something like that for the purposes of making, a later action figure, right? So not everything has to be digital. I mean, there's still a lot of hand artistry that goes into a lot of these things. You can see kind of along the top of this all of the recognizable, Harry Potter figures, and what else we got here? We got Harry Potter, we got Star Wars. I think I have a zoom in of that. So here are a bunch of these figures that all started from clay. Right? So what will happen basically is that these will be very carefully hand sculpted, and then they'll be 3D scanned in and used for printing later on. Right? There's also a lot of digital work to clean up these things for different purposes, and so it may be that you don't necessarily need all the detail that you get from a 3D scan of an object when you're making a toy or when you're making a video game character or something like that. And so you want to have enough detail to kind of sell the idea, but you don't want to have maybe every 3D vertex that you got from the scanner. And so there's a lot of digital cleanup work later by experts to figure out how to make, the scan that's at the right kind of resolution and the right quality for the job at hand. And so I don't have the picture right here, but this guy, when I visited, was working on I think it was going to be like I wouldn't call it a toy, like a figure for Venom after he's been totally bulked up, right? And so this artist was looking at these pictures of bodybuilding magazines, these crazy steroid bulked up guys, to figure out how he should edit the musculature of this object to make it look realistic, right? So it's not just like scan and print and go. There's a lot of people behind the scenes who are making it all work. So here, this is a head of Dennis Hopper from a scan of some movie or other that I'm holding on to. And so I got to say that this was possibly one of the coolest places I've ever been. So this is a totally unassuming, almost sketchy looking strip mall-like storefront in California in the middle of this kind of industrial district. So I kind of get to this address and I'm like, oh man, is this a mistake? Am I going to get murdered here in this alley? And then, I go in there and this is this incredible, it's totally geeking out of all the stuff that you see there. So these are all sorts of action figures that have been produced from different things. And so, all the franchises that so I mean, you probably have a friend who has a little thing on their bookshelf from The Matrix or from Star Wars, and this is where all those things are born, right? And not only that, not only are these things used for, toys and kind of tabletop-sized stuff, they're also used for Comic-Con, massive 10-foot tall, displays. So all that stuff is also born in the studio. And so you go in and you see this is a, Lord Voldemort that is 10 or 12 feet high sitting in their display room, right? This we got is a life-size mech from the Sucker Punch movie. You got your, 9-foot tall Na'vi from Avatar in the lobby. This is Sauron from Lord of the Rings. Again, just sitting next to you, but it's huge as life, So it was totally awesome. We got some Boba Fett thing next to a trash can, and me and Jabba the Hutt, right? So these are the kinds of things that you see at these big trade shows and so on. And again, they all come from different kinds of 3D scanning. And so again, my thanks to Steve Chapman at Gentle Giant Studios, who was the one who let me in the door and talked to me about 3D scanning. And so you can see in the back of the chapter, there's an interview with him about specifically things like LiDAR and structured light scanning for movies. and how it's changed over the years and what they use and what they don't use. So yeah, super cool trip. Okay, so where are we going from here? We have 2 more lectures, and then we're going to, so those lectures kind of get a little bit more back into the world of computer vision. So I mean, what I've talked about, 3D scanning definitely falls under the umbrella of what people talk about in computer vision, but let's talk again next week about what can you do when you don't have an active, so these are all what I would call active techniques in which you're interfering with the scene by pushing light into it, right? So you're definitely not just taking the scene as it comes, you're trying to probe it with different kinds of lasers and light. But you can do a lot with just taking lots of pictures of a scene, right? So we talked about in the dense correspondence chapter, or maybe it was the match moving chapter, if I want to get a 3D model of the Statue of Liberty, I can do something like structure for motion, where I take lots of pictures of it, I figure out where all the cameras are, I triangulate through all the corresponding points, and I get a 3D model, right? So that is kind of a technology called multi-view stereo, and that's what we're going to talk about on Monday. And then on Thursday, we'll talk about some of the algorithms that you need to work with these kinds of 3-dimensional data. So one big issue is registration. How do I take 2 3-dimensional point cloud data sets and fuse them together into the same frame of reference? Because as you can appreciate from what we saw today, there's lots of need to do that. Because just what we were seeing with the RTEC scanner, you're acquiring a bunch of partial scans. How do you register those together into the complete 3D mesh? Obviously, the job is easier when you have some co-located color on the mesh like we do in this case. So we'll talk about how that process works. And then that will be the end of the lectures. Okay, so any questions about anything? All right, then I will, I guess I didn't actually write hardly anything this week, so I didn't need my camera.